Hello. This is Nicholas, and I wanted to make just a quick video about something that I discovered before I go on my bike ride on this lovely Sunday. And that is, I was helping a friend with a calculus Taylor series homework, and one of the problems that asked about the classic Taylor series for natural log of 1 plus x, and that was x minus a half x squared plus a third x cubed minus a fourth x to the fourth plus or minus so on and so forth, right? And this should be not news to you, But so also one thing I'd like to point out is if you let x be equal to 1, you get the alternating harmonic series, namely that the natural log of 2 is indeed 1 minus a half plus a third minus a fourth, plus or minus, so on and so forth. That's just kind of a cool tidbit of information, although it's not really related to the point that I'm trying to make in this video. So now what am I saying here? So natural log of 1 plus x, it looks like, wow, even for the straight line tool, those are some bad lines. So natural log of 1 plus x, it's got an asymptote right here at -1, and then it looks something like that. And it has, the Taylor series has a radius of convergence of 1. So it converges from -1, not equal to, -1 to 1 exclusive, for sure. So somewhere along here. If the Taylor series is centered at 0, of course, that's normally where you center it, is at 0. And what I found, I was just kind of curious, is, what if I center this instead at like negative 0.3, right? And I found that then in that case, at x equals negative 0.3, the Taylor series had a radius of convergence of 0.7. So in other words, just the distance from the x coordinate where we centered to the nearest vertical asymptote. And so I said, okay, let me explore this a little more. And so I came up with the function 1 over 1 plus x squared. And now this is it's continuous everywhere, right? Because this part on the denominator is always going to be greater than 0, or I wrote 1. It's always going to be greater than 0, and so it's going to look nice, right? It's going to look like something like a bell curve, something like that. That's a bad bell curve. Something like, you get my point. So now if you center this at 0, it turns out that there is a radius of convergence. Oh my gosh. If you center it at x equals 0, I don't know why I'm drawing it up there. At x equals 0, you have a radius of convergence of 1. If you center it at, say, x equals 1, though, you end up having let me write. At x equals 0, we've got a radius of convergence of 1. But at x equals 1, it turned out, and you can go through the math yourself here, turns out we have a radius of convergence of the square root of 2. And I said, well, why are we getting square root of 2 there? What's so special about square root of 2? And so I was plugging in numbers kind of in between here, and I was getting some wacky stuff out. Like I plugged in x equals 0.3 or something, and I remember getting a radius of convergence of like 1.07 or something like this. And I said, well, I see the math here and I see what I'm doing. And so, I guess, it's right. But in other words, why? Where are these numbers coming from? What do they mean? And so what kind of hit me was that if we were to imagine this function, say 1 over 1 plus x squared, and we're we're basically to turn this function. Right now it's f. It takes a real variable input and gives you a real variable output. So it's two-dimensional, right? One-dimensional input space and one-dimensional output space. If we're instead going to take it from a two-dimensional input space to a one-dimensional output space, where this input space is formed by C. In other words, we're going to let a complex number be entered into this equation, right, this function right there. So we would have something like, now the function is going to be in 3 dimensions, but I'll draw the input space. So for the input space, we have the real axis and then the imaginary axis. And so if you notice, of course, this function here that we've taken and basically added a dimension to its input space where we've included the imaginary axis is perfectly okay, because it's just a generalization. This is just a generalization of this. And we can see that because on the imaginary axis, if we let, quote, y be equal to 0, right, then we just get this real axis, and that's where we were before. So we're basically just extending this function for complex numbers as well. So now what we're going to do with that is notice that at what? At this would be I and negative I, right? And at those particular points here and here on this complex number 3D plot of the function, it's going to not be defined. There are going to be, in the complex world, asymptotes for this function that is continuous everywhere in the real variable world, right? And so you see that, right? Because 1 over 1 plus or minus I squared is going to give you 1 over 0, right? And so you're going to have asymptotes at those particular points. So I said, well, that's interesting, and it kind of hit me all of a sudden, because now at x equals 0, sure, 1 makes perfect sense, right? It's just the distance nearest to the closest complex asymptote. At x equals 1, it still makes sense. Again, it's just the distance nearest to the complex asymptote. And you can see that, right? This is 1, and so Pythagorean theorem, that's the square root of 2. And likewise here, that's the square root of 2. And so the radius of convergence, and this also explains why it's actually a radius of convergence, we define it as the distance of a circle centered at the point in which you're centering your Taylor series, the minimum radius needed to reach the closest complex asymptote to your center of your Taylor series. So with a radius of the square root of 2 at x equals 1, we would be touching those 2 points. And we'd just be touching them, right? Wouldn't be going over them or anything like this. Oop. So, I'll use this tool. Try it like this. Okay. And so at x, with a radius of the square root of 2, that is the minimum radius to touch this point and this point. And that explains why we prefer radius of convergence over just, say, region of convergence, right? Because it literally is a circle, right? It's a circle, so I'll write it out just to be super clear. Radius of convergence, more generally in the complex world, when you get to things like complex analysis and things like this, it's defined as the minimum radius of a circle, and it's going to be centered at, say, x equals a. That's where you're centering your Taylor series. Such that the circle is, quote, tangent, you could say, or touching the nearest complex asymptotes, or asymptotes, with F having, you could say, domain in C, the complex numbers. And so this was really cool, I thought, because if you consider complex numbers, then the meaning for the radius of convergence makes perfect sense. And it gives a natural meaning to what the name is actually talking about. Now, actually proving this, I cannot do for you right now. It requires a good bit of graduate level math that I just don't know right now. But the actual concept, I think, is still cool enough to make a video out of. I hope that you've found this helpful. And with that, I think